Hello everyone and welcome to Algorithmic Gems. In this series, I talk to computer scientists and software engineers about advanced algorithmic ideas that you won't find in typical programming or algorithms textbooks. They reside, however, in the minds of the top problem solvers and are basically what sets them apart from the rest of the crowd. Alright, let's get started. So let's look at this simple tree structure. I've numbered the nodes in the order they will be visited by a depth-first traversal, which basically means that starting from the root at the top, we traverse the tree from left to right, going deep whenever we can. Our algorithmic gem for today, which I call depth-first order, means that as part of the depth-first traversal process, we record when each node enters and exits the process. So in our example here, the depth first traversal starts at node 1 at time 1, then proceeds to node 2 at time 2, and then exits node 2 right away at time 3, and enters node 3 at time 4, and so on. Fast forward to cover all nodes, and we have the numbers in green, indicating when we entered and exited each node. Now, a good question is what does recording enter and exit times of nodes in the depth first traversal give us? Well, if you look closely at the numbers in green, you will notice that the enter time of each node is less than the enter time of any node in its subtree. Similarly, the exit time of any node is larger than the exit time of all nodes in its subtree. This means that if we order nodes in one line by their enter times, then we can use the enter and exit times of any node to locate a segment on that line that contains only the node subtree. For instance, node 3 has enter time 4 and exit time 19. If we look up 4 and 19 in the ordered list of nodes by enter time, we can locate the marked segment representing node 3's subtree. Obviously, we can use binary search to do the lookups efficiently. So our gem today, called depth first order, allows us to look at a subtree of nodes as a one-dimensional segment on a line. Let's see an example of how that can be useful. So let's assign a value to each node in the tree. I've written values in green here. Now the question is, calculate the sum of all values of nodes in node X subtree, which are at distance d from root. For instance, the sum of nodes at distance 3 from root, which live in node 8 subtree, is 14. Um, Basically nodes 9 and 10. A straightforward approach to answer those queries is to perform a depth-first traversal of the subtree of each query and sum all values at the required distance. However, this approach becomes very inefficient either in terms of time or space complexity if we need to answer a lot of these queries and if we have many nodes in our tree. So how can we do better here? Yep, you guessed right. Use today's gem, the depth first order. Basically, for each level from the root node, we need to build a list of nodes at that level, sorted by their enter time, and keep the cumulative sum at each element in the list. Now, to answer the query asking about nodes at level 3 that live in the subtree of node 8, we can locate node 8 segment on the level 3 list and subtract the cumulative sums of the segment start and end points to get our answer in a nice logarithmic time. Alright, that's all for today. I hope you enjoyed the beauty of today's algorithmic gem. I would love to hear your comments and feedback. Till next time.